Take a moment and really look at this image. What you are seeing is not an artist's impression or a computer simulation. This is a real photograph of a single atom transforming into a quantum wave. It is the clearest image ever captured of this phenomenon, and it represents something truly remarkable. For nearly a century, quantum mechanics has told us that particles can behave like waves. This idea has lived mostly in equations and thought experiments. We accepted it because the math worked, but actually seeing it happen, watching a single atom spread out into ripples of probability, that is something entirely different. The shape you see forming is called a wave packet. Think of it like dropping a pebble into still water. The ripples spread outward in a predictable pattern. But in this case, the ripples are not moving through water. They are the atom itself, literally spreading out into multiple places at once. This image bridges a gap that has existed since quantum theory began. On one side, we have the mathematical framework that describes how the quantum world behaves. On the other side, we have the observable reality we can actually see and touch. For the first time, those two worlds have met in a single photograph. Scientists have captured individual atoms before they have also measured wave behavior indirectly through experiments. But this image shows the transition happening in real time. You can see the atom existing as both a distinct particle and a spreading wave simultaneously. The implications extend far beyond just a cool picture. This type of quantum behavior is still poorly understood. Having clear visual evidence gives researchers a new tool to study these exotic phenomena. It opens doors to better quantum computers, new materials, and deeper understanding of reality itself. When you look at this image, you are looking at the moment quantum theory became quantum reality. Let us talk about one of the strangest ideas in all of science. Imagine you are holding a tennis ball. It is a solid object, right? You can throw it, catch it, and predict exactly where it will land. Now imagine that same tennis ball suddenly turning into a ripple spreading across a pond. That's essentially what happens in the quantum world, and it has baffled scientists for over a century. This phenomenon is called wave-particle duality. In the early 20th century, a French physicist named Louis de Broglie made a bold proposal. He suggested that matter, things like electrons and atoms, could behave as waves, not just light, but actual physical stuff. The scientific community thought he was crazy, but then came the famous double-slit experiment when researchers fired particles at a barrier with two slits. Something remarkable happened. The particles did not just go through one slit or the other like tiny bullets. Instead, they created an interference pattern on the other side. That's exactly what waves do when they pass through two openings and overlap. The ripples interact with each other, creating distinct bands of light and dark. Here's where it gets truly mind-bending. When scientists try to observe which slit each particle went through, the wave behavior vanished. The particles suddenly acted like particles again. The mere act of observation changed how reality behaved for decades. This duality existed mostly in equations and thought experiments. We accepted it as truth because the math worked beautifully, but actually seeing it happen, watching a single atom transform from a discrete dot into a spreading wave packet, remained out of reach. The technology simply was not there until now. So how exactly did scientists pull off something that seemed impossible for decades? The breakthrough required an elegant combination of trapping technology and laser precision. First, researchers had to isolate individual atoms using electromagnetic traps. These devices create invisible cages that hold single atoms in place, preventing them from interacting with anything in the environment. But trapping was just the beginning. The real magic happened with precision laser systems. Scientists directed carefully tuned laser pulses at these trapped atoms, essentially programming their quantum states. Think of it like writing code. But instead of computers, they were writing directly onto the fundamental building blocks of matter. The lasers served multiple purposes simultaneously. They cooled the atoms to near absolute zero, reducing any unwanted movement. They also manipulated the atoms into specific quantum configurations, preparing them for the wave transition that researchers wanted to observe. Here is where things get incredibly tricky. Quantum states are notoriously fragile. The slightest interference from outside forces causes something called decoherence. Basically, the quantum behavior collapses back into classical behavior before you can study it, so scientists had to maintain perfect conditions long enough to capture the transformation. The imaging system itself had to be revolutionary. Two traditional microscopes cannot see quantum effects directly. The team developed a detection method that could observe the atom without disturbing its quantum state. This required measuring the electromagnetic signatures the atom emitted during its wave transformation. The timing had to be precise down to nanoseconds. Too early, and you miss the transition entirely. Too late, and decoherence has already destroyed the quantum effect. The researchers essentially created a quantum camera shutter that operated on timescales almost too fast to comprehend. What they achieved was more than just a photograph. It was a window into reality at its most fundamental level, proving that we can now watch quantum mechanics happen in real time. Let us take a closer look at what this image is actually showing us, because honestly, it is pretty mind-bending when you understand what's happening at the center of the image. You will notice a bright concentrated spot. That's our atom in its most particle-like state. It is localized, meaning we can point to it and say, there it is right there. This is the classical view of matter that we are all familiar with from everyday life. But here's where things get weird. As your eyes move outward from that central bright spot, you will see the intensity begins to fade and spread. It does not just stop abruptly. Instead, it ripples outward like a stone dropped in a pond. These ripples are what physicists call a wave packet. Essentially, a series of overlapping waves that together describe where the atom might be found. The colors and brightness gradients you are seeing are not just artistic choices, they represent probability. The brighter regions show where the atom is more likely to be found if you were to measure it. The dimmer spreading regions show areas of lower probability. It is like a map of possibilities rather than a snapshot of a definite position. Now you might be wondering, are we actually seeing the wave function itself? Well, not exactly. What we are seeing is more like a shadow of the wave function, a visual representation of the probability distribution. The wave function itself is a mathematical object that exists in an abstract space. We cannot photograph it directly, but what we can capture is how that mathematical reality manifests in the physical world. This image bridges two seemingly incompatible views of reality, the particle and the wave coexisting in a single frame. It is quantum mechanics stopped mid-motion, frozen in the act of transformation. Let us take a moment to really think about what we are seeing here. This image is not just a technical achievement, it strikes at the heart of one of the deepest debates in all of physics. For nearly a century, physicists have argued about what quantum mechanics actually tells us about reality. The Copenhagen interpretation, largely developed by Niels Bohr and his colleagues, suggests that particles exist in superposition. Until we measure them at that point, the wave function collapses into a definite state. But this new visualization challenges us to think more carefully about what collapse really means. We can actually see the transition happening. Then there's the many worlds interpretation. This view suggests that measurement does not collapse anything. Instead, all possible outcomes occur each in its own branching universe. When we observe an atom morphing into a wave, are we witnessing reality splitting before our eyes? It is a provocative question that this imagery brings to life in a way equations never could. The pilot wave theory offers yet another perspective. It proposes that particles have definite positions at all times, guided by an invisible wave. This image seems to give that idea some visual support. We can see what looks like a particle being carried along by its associated wave pattern. What makes this so profound is that we are no longer dealing with abstract mathematics or thought experiments. We have direct visual evidence of the transition between particle and wave states. This forces us to reconsider what we mean by measurement itself. Is the camera measuring the atom? Is it triggering decoherence? Or are we simply catching a glimpse of nature's fundamental fuzziness? These questions do not have easy answers, but now for the first time we can see what we have been arguing about all these years. So what does this breakthrough actually mean for the future? The implications stretch far beyond just capturing a stunning image. This capability opens doors to technologies that were purely theoretical just decades ago. Let us start with quantum computing. One of the biggest challenges in building practical quantum computers is understanding exactly how quantum states behave and evolve. Until now, researchers have been working largely with mathematical predictions, but with the ability to actually see wave packets forming and changing, scientists can verify their models in real time. They can observe how quantum information might degrade or shift and develop strategies to protect it. This could accelerate the development of more stable, more powerful quantum computers by years, if not decades. Then there is quantum sensing. These are devices that use quantum states to make incredibly precise measurements. Think sensors that can detect magnetic fields thousands of times weaker than what we can measure today, or gravity sensors that can map underground structures without digging. The detailed observations made possible by this imaging breakthrough could help engineers design quantum sensors with unprecedented sensitivity and reliability. But perhaps most exciting is what this means for atomic scale manipulation. If we can see how atoms behave as waves, we can learn to control that behavior. We might eventually engineer materials atom by atom, creating substances with properties we can barely imagine today. There is also the deeper scientific value. Quantum behavior at this level is still poorly understood in many ways. Scientists have debated interpretations of quantum mechanics for a century. Now, they have a window into watching it happen nearly 100 years after Schrödinger wrote his famous equation. Humanity finally has eyes to see the quantum realm. We are no longer just calculating what should happen, we are watching it unfold, and that changes everything about what becomes possible next.